Hey everyone, welcome to this explainer. I am so thrilled to have you here today. We're going to completely unpack the future of building automation. And look, we're moving way beyond the days of just slapping a simple thermostat on a wall, right? We're talking maximum energy efficiency and absolute precision control. Today is all about what happens when the high-speed, deterministic logic of an industrial PLC crashes right into the macroscopic strategic brain of a building management system. It is going to be awesome.
Okay, let's dive right into this. The era of simple on-off HVAC control, it's over. And honestly, it is about time. For decades, buildings just relied on these legacy systems that essentially slammed heavy equipment on and off. It created terrible inefficiencies. But today, welcome to the intelligent building. We're dealing with incredibly sophisticated facilities that demand absolute pin-drop precision to maintain exact temperatures, humidity, and indoor air quality. All while ruthlessly cutting energy consumption. We absolutely need industrial-grade intelligence. So here's our roadmap for today. We're going to start with the three-layer architecture, move down to field devices and the AHU, explore PLC precision and PID, tackle industrial protocols, and then finally wrap up with BMS supervision. All right, kicking things off with Section 1, three-layer architecture. This is really the blueprint for intelligent automation. So our entire architecture flows sequentially through three very distinct layers. First up, right at the bottom, we've got the field level. This is physical reality, okay? The actual sensors gathering data and the actuators ready to make a move. Second, we step up to the automation level. This is our PLC. It's the machine brain taking all that raw data and making split-second logical decisions. And finally, we ascend to the supervision level. This is the BMS server and the operator workstation. It's where facility managers actually sit down to monitor trends, tweak schedules, and optimize the whole building as one massive holistic system. Moving right along to Section 2, field devices and the AHU, basically the physical layer of the air handling unit. Now, inside a modern AHU, the environment is just packed with specialized devices. On the input side, we are constantly pulling in live data from temperature, humidity, pressure, and CO2 sensors. All this raw physical data gets wired directly into the analog and digital input modules of our controller. Now, on the flip side, the PLC uses that exact data to command variable frequency drives, or VFDs, which precisely control the exact speeds of our supply and return fans. It's also commanding damper actuators to mix outdoor and return air, and it's modulating control valves to let the precise amount of chilled or hot water into those coils. It is quite literally a highly coordinated physical dance.
Which brings us to Section 3, PLC precision and PID, the deterministic brain in the machine.
I really want to highlight this fantastic quote from our sources here. Quote, "The biggest difference between an industrial PLC and a standard PC is the repeatability and determinism of the code." End quote. Guys, this is absolutely fundamental. Think about your standard laptop for a second. It might randomly pause what it's doing to run some annoying background update, right? You absolutely cannot have that happen when you're controlling heavy industrial fans and high-pressure valves. A PLC is deterministic. That basically means it makes a rigid promise that it will evaluate its logic in an exact, guaranteed time frame every single cycle without fail.
And this brilliantly illustrates how this deterministic brain actually functions through what we call a relentless PLC scan cycle. First, it reads all the inputs, snapping a perfect, instantaneous picture of the current state of every single sensor. Second, it executes the program. It literally reads the ladder object top to bottom, left to right. Finally, it updates the outputs, firing off new commands to those valves and VFDs. And the crazy part? It does all of this incredibly fast. We're talking usually in just 1 to 2 milliseconds. It's just this endless, ultra-high-speed loop of read, evaluate, and react.
But, sometimes running as fast as physically possible actually isn't what we want. Enter the cyclic interrupt. This is a highly specialized organization block inside the PLC. So instead of running every single millisecond, you can actually tell the PLC, hey, run this specific block of code at a perfectly exact but slower interval, say exactly every 500 milliseconds. Now you might be wondering, why does this even matter for HVAC? Well, complex math like PID temperature control needs a steady, precise time delta to calculate correctly. If you try to evaluate a temperature loop every single millisecond, the mathematical adjustments will just go completely erratic. By safely placing our PID logic inside a cyclic interrupt, we get incredibly stable, smooth control over time.
So the crucial point here is the stark contrast between those clunky legacy systems and modern automation. It all comes down to control.
Legacy on-off control basically just waits until a room gets way too hot, blasts the AC at 100%, completely overshoots the target, turns off, and then just waits until it gets too hot again. It's this jerky, totally unstable roller coaster that wastes a massive amount of fan power. But look on the right. We have PID control. This is smart. It actually predicts system behavior. It gradually adjusts those VFDs and valve positions, gently guiding the temperature until it stabilizes perfectly. And I mean precisely at our set point.
All right, let's actually break down the math behind this PID logic. P stands for proportional. Think of this as the immediate reaction to the current error. If a door suddenly swings open and a huge rush of hot air comes in, the P reacts right away. I is for integral. This one looks at the past. So if we're stuck just say half a degree away from our set point for a long time, the integral component slowly builds up and pushes to eliminate that stubborn steady-state error. And D stands for derivative. It looks at the rate of change, to essentially predict the future. If the temperature is dropping really fast, the D will actually start pulling back on the cooling early so we don't overshoot our target. Working all together, they handle stuff like a sudden massive increase in room occupancy flawlessly, totally avoiding any overreaction.
Okay, moving on to Section 4, Industrial Protocols. This is the nervous system connecting all our layers.
To actually share all these amazing deterministic calculations, our PLC typically uses one of these two major protocols to talk to the BMS server. Over on the left, we've got BACnet/IP. This is heavily used in building automation. It's a standardized, object-based protocol which just makes it incredibly robust for managing complex building data, things like schedules and alarms. Now, on the right is Modbus TCP. This is your classic industrial protocol. It's register-based, which means it is absolutely fantastic for rapid polling of live data points. Like if you need to quickly grab the exact speed of a fan or the exact position of a valve, Modbus is your best friend. Both of these protocols ensure that live values and data packets move seamlessly from the PLC switch all the way up to our server.
And finally, we arrive at Section 5, BMS supervision, the macroscopic brain of the building.
So while a PLC is amazing at controlling a single localized machine, the building management system is what controls the entire facility. From the operator workstation, a facility manager gets some seriously advanced capabilities. I mean, they can pull up beautiful 3D graphic overviews of the AHU and watch live trend graphs in real time. The BMS can perform automatic set point resets based on the outside weather, seamlessly executing seasonal optimization and summer/winter modes. It leverages scheduling and demand-based ventilation, so we're only conditioning air when spaces are actually occupied. It even uses all this data for predictive maintenance and fault detection. But most importantly, it allows for multi-AHU optimization, ensuring the entire building is operating in perfect harmony to meet those really strict ISO 50001 energy standards.
Now, what's really interesting about this slide is just how dramatic the results are when the PLC and BMS are perfectly integrated. Just look at the before and after. Before optimization, electrical consumption was sky high and fan power was just constantly blasting at maximum. After optimization, consumption is drastically reduced, primarily because our fans are now variable. They're driven by VFDs to use only as much power as absolutely needed. The coefficient of performance jumps from terribly low to incredibly high. And as for the actual people inside the building, they go from sitting in a fluctuating, uncomfortable environment to one that is just flawlessly stable.
As we wrap up this explainer, I want to leave you with a bit of a provocative question to chew on. When you look at the sheer complexity of the field wiring, the ultra-fast deterministic logic of the PLC, and then that macroscopic, overarching network of the BMS, what do you think is the biggest technical challenge when integrating a newly programmed AHU PLC into a massive, already existing building management system? Is it trying to align those network protocols? Is it meticulously mapping hundreds of data points? Or maybe it's ensuring that the new PID tuning actually respects the legacy systems already in place? I want you to really think about it and let it drive your curiosity to dive even deeper into this incredible world of automation engineering. Thank you so much for joining me today, and as always, keep learning.